So greetings from Cologne. My presentation is, pumps and pump systems. David asked me to keep it as basic as possible because pumps is actually a science topic for a complete conference itself. So I will talk about some aspiration vacuum. Tommaso called it volume or pulling vacuum. There are some different many pumps, and these are my disclosures. And Archimedes featuring Hagen-Poisson, it actually fits very, very well the topic, because Archimedes has been the first one to invented this spiral documented first pump. And this is actually still on work. It's not so far from here. It's still a concept that actually works for pumping high volumes of levels of water from one level to each other. In a single set, you can see how many different pumps for creating aspiration are in the market. The most familiar we are working out are the volume pumps, the pressure pumps, the Venturi or Bernoulli effect. We all know that from the physics in school. We have a smaller area in this part, a bigger area in this part, and the velocity increase and the pressure decrease here in comparison to this area. So you use this pressure decrease to create this vacuum, and then we have this volume movement pumps, which is the peristaltic pump. Peristalsis is something also we have in our intestinal tract. So we're moving fluids, which is actually a mixture. It's never only moving a fluid, it's creating also a vacuum on the distal part of the part. So it's in combined. That's why most of the pumps has a maximum. That's why we see a limit of 600, 760 or 680 in our pumps. And, it's based on the atmospheric pressure. This is the limit what the pressure can give us as a contradictive power to create vacuum. So this is also based on altitude because of atmospheric pressure, and we are if you are on the top of Mount Everest, we have really low vacuum to do our vitrectomy. It doesn't recommend to do that. Stay in our level or in Amsterdam. I suppose we are -1 meter or 2 meters here, so we have better vitrectomy results with higher, greater pumps here. So that's around the limit of the maximum vacuum we can create, 680. And then we need to talk about pumps and chamber stability, because it's a complex used together. We have AC, the anterior chamber and the posterior chamber. They are completely different. The AC is more flexible, more variable to pressures, and the posterior chamber is much more stable, thicker walls and less moving parts. I call this the ACPC system. So the optimizing the fluidics, we see here the peristaltic pumps. It's a very simplified diagram which shows a linear increase of maximum 680 in 4 to 5 seconds. That's why it's a very stable and linear increase of vacuum, And then we have the Venturi aspiration, where we have a really fast creation of a vacuum in 1.4 seconds, but it's an exponential one. So it's not linear, it's not easy to control. You're pressing the foot pedal and you see some reaction later. And then you have the interaction of the vitreous in the BSS, and you have your vitreous scatter inside the vitreous bubble. We have the Hagen-Poisson equation. We have the P, which is the only stable constant in this equation. We have the length of the system, which is not only the kata, but the complete length to the machine. Then the radius of the diameter, in this case, the radius of the system, the viscosity, and the differential of pressure, which is actually our vacuum creation, which is created from the machine to the tip. This is the delta P, the difference of pressure. Most systems worked with vacuum-based. Most vacuum pumps work with vacuum control. So your foot pedal just control the vacuum, and you're creating 0 to 680 by pressing the foot pedal. If you go peristaltic, you imagine you're working in a vitreous bubble with 400 millimeter of mercury to be secure. And then the vitreous is done, is carried out, and immediately you get in the BSS, which changes the viscosity. You see the N. And this, according to the equation, immediately changed the pressure the vacuum of the pump. The pump reacts and gives you much more vacuum, which of course in sometimes can be tricky, very close to the retina and all these alterations. Even more, if you go to the Venturi pump, if you lose the contact to the vitreous and go to a viscosity which is smaller with a BSS, then you immediately have almost a maximum vacuum. This could be really dangerous if you are close to the retina. And the normal action of the vitreous cutter, it's a journey between different viscosities all the time. We have lagoons of BSS, lagoons of vitreous, and this journey is permanently changing between viscosities, and we have permanently changes in the vacuum. Especially if you go from vitreous to air, or if you make BSS exchange to air, and you are in vacuum mode, you can completely lose the pressure in the eye because you have an increase of vacuum, which is unexpected, especially with a Venturi pump. So this is the same thing with the detached retina. You see also in the peristaltic mode, we have some oscillations because of the rolls and the gaps between the rolls. And these oscillations are very small, not so thick like the yellow line, but you could perhaps see it if you have by movement of the vitreous in the detached retina. You see here a double cutting system and a single cutting system. You see these peristaltic movements also from the cutter. So, and of course, if you lose the vitreous there and you go to BSS, the vacuum will increase, you will cancerate retina, and even worse if you were in vacuum mode. So what to do? Just the modern vacuum pumps just change the equation. Keep the flow, the vacuum keep the flow stable. So you define how many cc's per minute you want to remove and let the delta P change. That's how the new motor pumps work. So if you press the foot pedal, you just change the wanted cc per minute, and the machine calculates with the software the differential of vacuum. This is permanently playing around, depending on if you are on the vitreous or if you are in the air. You see, now we have a completely different scenario. We lost the contact with the high viscosity material, and immediately the pump calculates down to remain the flow stable. That's same and more crucial also to the Venturi pump. That's the definition of flow control. So you're keeping your cc per minute constantly, letting the software calculates your around. And of course, we have also other instruments like new cutters, where we have another scenario there. We have the flow, which is the Q in this, and delta P, and we have cutters which increased the flow tremendously because the diameter is higher. And according to this equation, the delta P of the tip is higher, so the force you have on the cutter is higher. That allows 27 gauge cutters to do PVD easier because the delta P, the power of the tip is higher. You have greater power from the vacuum pump with this type of cutters to grasp and make diabetic delaminations. You can control the cutter as a forceps because of this delta P and this vacuum creation. And this is getting all the procedures more safely and faster. You can delaminate, you can make the visual skies. It's based also on flow control and keeping the difference of the vacuum high. If you remove some dropped nucleus, this double cutting opening system with the flow control mode will keep you the particles in place. So increase safety, flow, the differential of pressure, increase the pressure and the strength of the cutter. And there are some sophisticated softwares and machines out there that allows very precisely flow control, and which gave us the biggest benefit to go and shave in a detached retina, and with a machine which permanently calculate the vacuum creation according to the wanted cc per minute. In this case, you can go to 2 cc per minute, which is, or 3 cc per minute, which is really low, with a very, very small diameter cutter, 27 gauge, and shave a detached retina in very safe mode. And you still see some movements there, which is a cutting system. Decreasing the cc per minute, we have two. Please look at on the left downside, 2 cc per minute. You can really go and carefully shave the Dutch retina, and that's based to these modern flow control pumps. That was a small overview of the systems are available, and the future is it's great. There are many things to optimize in pump systems. We had a great discussion yesterday and hope to keep on discussing on the topic. Thank you.
Thank you, Fanis. Just give some general guidelines for, do you always use a flow control pump for every step of your vitrectomy, or do you ever use vacuum control?